Okay. Hello everybody. Welcome to my talk. Good afternoon to everyone. So, I'd firstly like to thank everyone for being here, and I'd like to thank Dr. Ling for his role as my advisor during this journey. I really found really helpful. Thank you for Professor Rahmati for agreeing to be the chair, and thank you, Dr. Tan, for your input over the entire journey too. Okay, my topic is basically identifying unauthorized computer vision models in Android phones. And for this, we set up an experiment. We defined the problem, and we got the results of the experiment, and we aim to publish it in the future. So I've been working on this since January, and I think uh, the group members, Sarah Lemon and Dr. Tan, have been, and even Dr. Ling have been working on this prior to that. Um, so just going into the background before we begin the topic actually. So augmented reality is going like progressing really fast. Even in the latest technology releases, augmented reality is mentioned a lot. iPhones have the lidar sensors, which they especially built in for augmented reality applications. We can then another, even Google smart glasses were actually, they came out in 2012, but there are more augmentation technology available now than it was in the previous period. We so basically the thing is with humans is that we are limited by our brains on how much we can recall, how much we can store, and how much information we have at our fingertips. So
Hỏi con em
augmentations really help with that.
con em bảo vệ luận văn đấy, nghe thấy cái gì nữa.
Somebody's not muted. Okay. So augmentations really help with that. There are like a few examples are smart glasses, smartphones, Neuralink. Like smartphones, Google Maps has a feature where you can just point around you, and Google Maps will point you in the direction where you should go. And so the thing which is enabling everything is cameras and processors. Processors are becoming smaller, cheaper, and much efficient and better. So this is enabling augmented reality to be widespread. And another thing is, so another part of the new reality is edge computing. So we have phones, on our phones there is a neural uh, NLP model always running to hear when we are saying okay Google or hey Siri. And these devices are always on, and they require very low power, but they are continuously running in the background. And this is due to computing power has reached at a level so that it is not, the user experience is not damaged if something is running in the background. And also the machine learning models are becoming efficient, small, and the accuracy is still very accurate. So the thing we need to remember while going into the future is, uh, so if somebody is collecting data from users, then they might not just gather a stream of video and then store it and then process it later. They might just gather inferences from such machine learning models and then store the extremely small inferences in their database. And the thing is, inferences, so companies might, it is also much more user friendly to compute inferences at the edge if they are providing it in the providing it as for targeted advertisements, because bandwidth is limited but processing power is not. So our aim is to basically identify whether a computer vision model is running in the background of an augmented reality application without the user's knowledge. It might have permission actually, but without permission is um, can be detected too. So basically, we have these following 4 or 5 steps. We define the problem, we set up an experiment, we gather the data in the bounds of that experiment, then process the data, and then we have the results now. So while while we go into the experiment, we are trying to detect whether for a particular scenario the app is behaving maliciously or not. We cannot really detect whether there is malicious functionality built into the app. There are destructive ways of, there are approaches which are a bit destructive, in which the app is decompiled and You can just go into the app and then try to identify what it is doing. But this is a black box approach, and the app does not is not notified when we are performing the testing. There is no way for the app to know that we are doing this testing. So here actually I have an example of an augmented reality application, which a Snapchat. So basically what I did is I pointed the app at my face, and approximately at the 1 minute mark, I turned on the augmented reality features, and it computed the 3D geometry of my face. And then after this, I enabled the filter, and you can see that the initial CPU values, CPU readings are much lower, and there is a huge spike while calculating, while there is some processing going on. And in the end, there is just a elevated CPU usage by the application. So this is basically a proof of concept that we can detect what is going on in the app by just changing the external factors. And by giving the right external factor, we hope to detect whether the app is performing something, trying to identify something malicious, some privacy, trying to compromise privacy for the users or not. So here's the problem definition. So we represent an app by X, and it basically has these functions, A naught to AN. A naught is just the combination of all the non-computer vision functions, and A1 to AN are just all the functions which are related to computer vision and which we are hoping to detect. So for the scope of this experiment, we are just limiting for the safe app. So we created the apps ourselves, and for the scope of this experiment, we just have one computer vision function in the safe app and two computer vision functions in the malicious app. And this function C of XS, that is basically what the app claims to do. So for the safe app, it claims that it is performing these A naught and AI tasks, and AI is basically what they claim to do. And for the malicious app, it is doing an extra task, like something like age plus gender detection in the background, or eye tracking, where you are looking, and something like that. And it is still claiming to do just AI, like just the safe one. So we classify it as malicious or safe according to whether it is true to the set of what it actually does or not. And so now we define kind of the experiment and for like further define the problem. So M of xi is basically the vector, which is the system resource utilization log, and we also call it as a system trace or a CPU trace. So for an app xi for the experiment, so what we do is we feed input to it, and based on the changing input, we are going to observe some changes in the CPU utilization in the background, and we are going to try to identify whether an app is malicious or honest based on this CPU trace. So we have the baseline. We have three parts to the input, and this is in the form of a video because we are testing camera applications mostly, right? So the baseline just some solid colors, and this helps us to get a baseline estimation when just some detect interest region detectors are running, because most computer vision models have are two-step processes. So one is just it detects an interest region like a face, and then the next one goes and identifies the face or identifies the age and gender of that face, and stuff like that. So in the baseline, we just establish a baseline of the CPU readings, and the part one will trigger the claim model for the safe app and the malicious app. And then the part two will just trigger the hidden model in the malicious app. So, so again, like we will be recording this continuously, and based on these recorded values, we are going to try to estimate whether we are going to see whether we can estimate whether we can see whether an app is honest or malicious. So these are the three. This is just an example of the three inputs. This is like the solid colors for the baseline, where there is no interest regions present in the present to for the app to get detected triggered. This is an example of barcodes. So there is all the text has been blotted out, and just the barcodes are remaining. And this is just some text and no objects, just text on white background. So we for the purpose of this experiment, we have barcodes, objects, faces, and text. These are the four categories of computer vision models we hope to detect. So part zero will always be the baseline, as in the earlier slide. Just the part one and part two can be a combination of both of these. So over here, we have an ideal CPU graph for malicious versus safe. So as I said earlier, a baseline will be established for part one, the for the honest and safe, the malicious and the safe. Both of the apps, they will process do some processing because an interest region has been triggered. And for the malicious app, when the for the part two section part two, it will again boost and will not go back to the baseline. Like the safe app will just go back to the baseline afterwards. So this is an actual graph of the CPU values for the barcode and text example I had shown earlier. So this is just the honest app, which is divided into three sections, and this is just the malicious app, which is divided into three sections. The green lines are actually a bit shifted, but you can see there is a clear differentiation between the CPU values for each part. So the so one thing we needed to take into consideration is the input format. So what we did is just there are three possible input formats, right? So as usual, just via the camera, then we can record a video on the camera and feed it to the app from memory. And then the third thing is just create a video from images, still images, and feed that to the app internally. So recording a video or having the camera, that results in a bit of a jitter and some background noises. So we wanted to test whether all of these can give the same result or not. So we perform statistical analysis on this. I'll explain that in the further slides. And since this was at an initial stage, we did not have enough data to go through this via the neural network. So we are using machine learning. So using statistical approach, we found that it is we can detect malicious behavior even if regardless of the input format. So I'll just explain the statistical method as I mentioned. So what we do is, as we saw earlier, if we divide each of these CPU values into three separate populations, we can perform homogeneity tests to find out whether we can whether we can identify whether the two populations are at the same are of the same distribution or not. So for the safe app, the hypothesis is that the population of the CPU values for baseline and for the part two will be homogeneous. And the the second hypothesis is that for the malicious, we will find something like three different distributions, and none of them will be homogeneous. So what we did is we had two different tests. So one is the student t test, which is mainly used to identify difference between the means of two different population. And the Kolmogorov-Smirnov test also does that, but also uh, it can also detect dis- different distributions of the populations. So even if the mean is same, but the case test can detect a different distribution as well. So we have an ideal graph, we have the hypothesis, and we have the homogeneity test. So basically we gathered a lot of data and then do this. So to visualize the result from the statistical analysis on one CPU trace. So we had an honest app, which is just the barcode, and this data is from the barcode and text application, as I showed earlier. So what we do is we represent the uh, three populations as nodes on the graph, or as sections in the confusion matrix, and the p-values for the comparison is shown over here. So the confusion matrix is actually the most common way to represent this data, but I found that this it is not really you cannot understand it at a glance. So I just represented it in a form of a graph, and if there is a link in the graph, it means that the two populations are homogeneous, and the value is the p-value which is shown over here. So you can see this 0.375 matches with a comparison for the p-value for the comparison over here, baseline versus part 2. So this is just to visualize the result from one individual statistical analysis. So this is an example for the same barcode and text app. So the honest application had just the functionality for the honest application was just a barcode scanning, and for the malicious app we implemented barcode as well as text. So we saw this particular graph for the statistical analysis.
Sorry, one quick question about the graph. Shouldn't the numbers in each line and each column add up to 1? Why do you have
no, it does not have to add up to 1 because it is a p-value, so it goes from 0 to 1, and so over here you can see that the baseline the baseline versus baseline is 1 because it is the same population, so that's why it's 1. It's the p-value. This is just the initial result we got, and based on that we had the following app combinations. We had the barcode scanning plus text recognition, then object detection, and object detection plus text recognition. And this is the honest application, the functionality for the honest application, and this is functionality for the malicious application. So you can see actually the most of the malicious function is the text recognition, but so initially we had text recognition, like only text recognition running. So we started out with that, and later on age and gender recognition and any other model. So now afterwards we got an Android app. We created an app which can handle any tensor, just or any TF-Lite model which you can input to give it as an input. So we plan to actually expand the data set, but this is we did not have the time for it. So here actually this is a different confusion matrix. This is like just based on the hypothesis we had we gathered 52 traces, 52 CPU traces, and so half of the CPU traces were from honest apps and half of the CPU traces were from malicious apps. The video, the malicious apps, and basically we wanted to see whether we use statistical analysis to see whether we can detect what is the accuracy we get for when to detect malicious applications. So this is the this is the confusion matrix for that. This is like a standard confusion matrix. So the summation for this row will be 1, and this basically means that using the case test for the case homogeneity test, we got an accuracy of 84% while detecting malicious applications and 69% for detecting honest applications. So the true positives and false positives rates are quite high for this statistical approach. And even for the t-test, it's a bit lower than the case test. Okay. So the next approach we tried is just using machine learning and create a structured data set and see what results we get if when we train it and test using some data. So as I mentioned earlier, so we had 52 CPU traces, and 50% of the CPU traces were from honest apps, and the remaining 50% were from the malicious applications. Um, each CPU trace, for each CPU trace, we run the application. We have the video which runs for 9 minutes, and we record the CPU values for the 9 minutes. And these values are recorded using the top command, and we isolate the utilization values for the particular application, and it does not just um, record the entire uh, record the CPU values for all of the running processes, just for the one we want to track. So each CPU, so in this diagram, I have this is one CPU trace which is divided into 3 sections based on the 3 different inputs. So this is for the baseline, and for each section we have 6 images. So again, this is subdivided into 6 parts, and from this is just an example of a graph which we might see the CPU values. So um, yeah, so what we do is we sample just 30 values from each section. The app is running for 9 minutes, and we approximately gather we approximately the the fastest we can sample CPU values is like 100 per minute. So there is actually a bit of a variation. So that's why we need to sample it, because all of the CPU traces are not of equal length. And another thing is, if we want to, so this assumes that we are having, if we 540 for the particular model, we are having a input vector of 540. So we can reduce this later on if using this approach. So as I said earlier, uh, each the total trace is divided into 3. It is further subdivided into 6 for each image that is running. And for each image, we just sample 30 values, and though we compile that into a data set, and we do that 5 times to ensure that all of the variability of the CPU trace is captured, because remember, we are doing random sampling. So after this, we get a data set of we have 52 CPU traces, and we do that 5 times for each CPU trace. So we have a data set of 260 vectors. And for the labels, what we do is we have a multi-label binarizer format, and in that we have 4 columns. So each column just has a true or false value, and each row corresponds to the same row in the data set, the CPU trace data set. So the way we feed it, make this file, like map this to honest or malicious, is if 2 columns have true values, then the entry label is malicious.
On materials for...
Hello. Yeah.
Can you hear me? Sorry.
Oh,
no, can you hear me?
Yeah, I can hear you.
So I had a question here. So here you mainly focused on CPU traces.
Yeah.
Did you try augmenting your data with other sources such as memory usage or battery usage or other factors, and how that affected your results?
Yeah. So what we tried memory usage, but there was no correlation. Like we did not observe any correlation between the memory usage and the label. So that's why we dropped the memory. There are actually many other parameters which we can use, like flags from the system and stuff like that. So there was I read a research in which they try to detect whether a Bitcoin mining is being done on mobile device based on the flags. So this can be actually a future scope because we did not have uh, enough correlation. And first thing was the CPU values were we found that the CPU values were having a good correlation between the final maliciousness and the honestness. And also if we want to improve this, and maybe if the so the thing is, in the future there is a huge probability that the computer vision models are going to be much more efficient. So when we cannot detect using the current approach, we will need to have more data in the data set. We'll need to capture more data in the data set, but for now it's for an initial approach, it is the CPU values enough. So in the label, then again, uh, so we had true values. If we had if two columns have true values, then the entry label is malicious, otherwise it is honest. And this is the formula which was used. It's basically the same thing, just adding all of the values for the columns and subtracting one, and we get an honest versus malicious. So 0 is honest and 1 is malicious. This is a standard neural network, just a multi-layer perceptron with 4 layers, and these are the activation functions after each layer. These are the number of nodes in each layer, and we have a binary and cross entropy log loss, and we trained it using the Adam optimizer. So as I said earlier, we had 260 rows in the dataset. 33% of the dataset were used for testing, and the remaining was used for training. And we trained the neural network for 20 epochs with a batch size of 50, and we got an accuracy of 98% on the training set, and on the testing set we got an accuracy of 97.67. So here I have the testing result from the neural network. So one thing, these values change a bit based on the sampling for the training and testing, because of the because the data set is so small. So this is actually a bit of a future scope, that increase the data set, have more permutations and combinations for the different computer vision functions. And so over here it is detecting like apps as honest for with the accuracy of 100%, and malicious is being detected with an accuracy of 98. So that's pretty good, I think. And yeah, so again, so an average accuracy we achieved used from the neural network is 96%. And this is we can expand this research very easily, because as we add more computer vision functions, um, there we might be able to detect face and a separate malicious process as just age and gender. And as we go and explore that, we might there is a huge scope for improvement, because so for augmented reality is not really that pervasive as of now yet. So we have some time before this becomes a problem. And so another thing why this is important is, if we consider what data Google is gathering today, uh, this might be classified as a malware 10 years ago. So we just need to kind of be able to detect what is being gathered now. So after 10 years, we are not completely slaves to the uh, big companies. And another thing that is in the future scope is to create accompanying Android app and a web application. So somebody can just download the security Android app on their phone and open the web application. The app will stream the CPU values, the memory usage, utilization usage to the web application, and the user can just follow some instructions, and the video might play online, and the user might get the privacy score for Snapchat and any app they can just they can try with this. So that is in the future scope, and I hope we can work on it. So my collaborator, Sarah Lehman, so she is a PhD student. She has been working on this for a long time, and she plans to continue this in the future. So I think even I might be able might be involved in that too. So that's my presentation for today. Any questions?
Thank you, Kunal. I personally had a couple of questions. So you described here basically the use of a machine learning model to detect whether other models are running on the device or not at the high level. But you could argue that this is, and you're only basing this on the CPU data, right? So
for now,
you could argue that, is there something unique about detecting machine learning models here that differentiate your work from previous ones that have looked at similar approaches for malware detection?
So I read a couple of approaches for malware detection, and there are many applications which focus on privacy, and most of them are using API calls to identify what data is being gathered by an application. So based on those API calls, there have been static as well as machine learning and dynamic approaches to identify whether an app is malware gathering excessive data or malware or not. But so in most of those approaches, it is not a black box approach. So in one of the papers I read, they said that they are using an API calls to identify whether the app is whatever app they are testing is malware or not. But they said that there is a chance that the application can get and understand whether that it is being monitored and change its behavior. So this aims to solve that nothing is affecting the app itself. We are just calculating values, like gathering system resource utilization separately and trying to identify it while the app is independently running on the phone.
So let's say you have a malware application that has that is fronting as a regular app. Let's say a calculator that also, as you mentioned, that was a nice example, mine bitcoins in the back when the user is not working with it. So technically, there's nothing stopping your model from detecting that.
Definitely, it can do that as well. But so one thing to keep in mind is that just a minute, let me. So most computer vision models are when you run them on a CPU, on a mobile device, or even on a desktop, we can see definite appreciable increase in the utilization of the processing. So if an application is just an application like Bitcoin mining is CPU intensive, so processing intensive, so that might be detected. But just some application which is gathering data without using much CPU power, like just basic location data and stuff like that, that cannot be detected by this. But
so let's say I have a CPU intensive activity, and Bitcoin mining, by the way, is a processor activity. So if this is the case, if the malicious application is aware that you're running this system, wouldn't they be able to kind of like limit the amount of their CPU usage so they stay under the radar in this case?
They might do that, but the thing is, so for computer vision, you cannot hide the spike in it, and even for Bitcoin mining, it might just not be profitable enough to, for example, if a standard, if they're running, it might require like 700% of the total usage. So 700% means for each core it goes till 100%. So it might use
But these are all operations, right? I can,
Yeah.
let's say, to update, to kind of like do the processing through the model, you need 1 million calculations to be done.
Yeah, exactly.
I can slow down my calculation so it takes 15 seconds for that 1 million calls to go through, right? And in that case, your approach could be challenged, challenged and may not work as well as you expect here, right?
True. Makes sense. I'll keep that in mind.
Yeah, that's an interesting.
I never thought that it could be done, because whenever we just go through the computer vision model, we just say input and here's the output. Like that might be really interesting to see whether calculation can be slowed down enough to not be detected by any, not give any spikes.
Because let's say you have kind of like you're working on the camera feed. Of course, your processing rate will become slower. You can process fewer frames per second.
Yeah.
But at the end of the day, you are still able to do it while staying under the radar. So as kind of like a future work in this space, you should definitely try to explore what would happen if the attacker is actually aware of this system. And this goes for any task, right? Because I think, Habin, I mentioned this to Kunal when I talked with him as well.
Mm-hmm.
This is, for me, this is more of a general solution that you can say, okay, you can potentially detect malicious activities in the phone using these side channel informations, right?
Yeah.
And the CPU, how much processor you're taking, how much memory you're taking, maybe including even the API calls that is happening in the system. So it's definitely valid approach to try and say like, okay, let's model this, and then we basically have a fancy anomaly detector that can tell us if something is happening.
I don't know.
I think Ibrahim was just stabbed.
This is something we cannot detect.
but it's important to keep in mind what would an attacker, what would be the counter if the attacker is now aware of this.
That is actually a really good food for thought.
Yeah.
All right, so I asked too many questions. Are there any other questions from the portal?
Yeah, I have a quick one. So Kuno, I mean, when you show the response of the three things, I mean, there's a small time lagging, right? Time lag. So the delay. So what is delay caused by?
So most of the times it is caused by, like, it takes some time for, if an interest region detector is always running, but it might take some time for the actual model to come into the cache, and that might cause some delay. Like it needs to be like fetched from memory to the cache, and that takes some time. That might be, but not long, like hardly 1 second, not even that.
I see. Yeah, my understanding. Yeah, I understand that there should be a delay, but I didn't expect the delay is kind of longer, perceptible. So I thought it just can be easily ignored, but apparently it's not. Right? It's there. I mean, in your plot, right?
Yeah. Oh, yeah. So usually, and even initially, there is a larger spike. Maybe it was not visible in this plot. I think this plot was just offset from the x-axis. So
yeah.
Any questions from the non-committee members? All right. If not, I think we can move on to private Q&A in case the committee has any questions for Kunal. So if other participants can please leave the meeting.
Amir, do we have this private Q&A session?
I mean, if you have any questions, yes, but if not, we can through Kunal out as well and
Okay.
start discussing.
I don't know this because at Temple we usually have this private Q&A session, but at Stony Brook, I mean, the several I mean kind of such meeting I attended, none of them seems to have this session, so I just don't know.
But my assumption is that we do, but it's frequently skipped over, I believe. I mean, if I don't have any more questions, so if you don't have any questions, we can definitely move on to our own discussions.
Yeah, sure. Either way is fine. Let's see if do we need to wait for other guys to exit?
I think you can just remove them.
I can just kick them out, right? Yeah. Okay, let me remove it. Oh, okay. Okay, now we are safe.
All right. I mean, if there aren't any more questions, I think Kunal can leave as well. And then, do you have a way of contacting him so he can get back in?
I plan to put him in a waiting room.
Yeah, I can leave and then try to join again.
Yeah. Chiu, do you have questions? You are muted, so we don't know.
Oh no, I'm good.
Okay. So Kunal, I will put you in the waiting room, and after our discussion, I will let you in again.
Yeah.